you're done, just turn that microphone off.
How do you turn it off? Okay, here you go.
Switch there.
Turn
Make
it.
sure. Good.
Okay.
And you can advance with us, forward, backward.
That's it. Is the slide control? Okay. Okay. So today, me and my colleague John, Ryan, are going to present something about, at least we are trying to pull the attention towards doing something about the FPGA, which is Field Programming Gate Array, Field Programmable Gate Array. And this presentation is actually an attempt to draw some attention of the importance of it in a spacecraft and to the overall IV&V as such. So I'll do the first part of the presentation and John is going to conclude it, okay? So let's try the, okay, where's the control? Okay, here you go. So I'll try to present some of the basic things about the FPGA and then give you some examples of it and then try to see why are we at all talking about FPGA in a software IV&V environment. And then John is going to take over. So what is an FPGA? FPGA is a field programmable gate array. What it allows you to do is that you are given, you can think of it as a box full of components, basic components out of which make a hardware circuitry. And those components, when you connect in a certain way, gives you a certain functionality. The FPGA gives you the ability to connect and reconnect the components one time or many times, or as many times as you want. So this means that I have the capability to change the circuit on the fly. And I may not choose to have that option. I may have the capability to change the fly, but I don't exercise that option. That's also possible. Or I may not even have the capability to change on the fly at all. In that case, I am stuck with my first programming. It's something like writing a CD-ROM. You write it once and then you are stuck with it. So basically what FPGA allows you to do is that it allows you to program your chosen circuitry at your own facility. You don't need to go to any manufacturing site. You can do it at your home. And it is so prominent nowadays. It has gone into everything. Almost everything we do has an FPGA. If everyone is carrying a cell phone, yeah, it has a number of FPGAs in it. Okay. So let's go to the next one. So here are the basics of the FPGA and what are the general classification, like it is either one-time programmable or it is many times programmable. In the many times programmable, what you see is that it could be anti-fuse based or flash based or SRAM based. The EEPROM style is kind of going away. And you know that there are the two prominent makers of FPGA, Xilinx and Actel and Microsemi. And also there are other companies involved, like the other guy is an FPGA, like the famous CPU maker. Okay, I'll come to that later on, but what it means is that some of the CPUs, some of the FPGAs they have CPU in it. You can have a CPU-based FPGA. It's not all that expensive. It's about $12, $13, and then you have a CPU-based FPGA. You have a CPU. How good or powerful is the CPU? It is an ARM Cortex. ARM Cortex CPU runs at 80 megahertz. It's probably as powerful as the RAT 750. So you have a lot of capability within that FPGA chip. And so the thing is that you can have a CPU or you may not have a CPU, but you have a large number of your basic components available. If you have a lot of basic components available, well, you can connect them up and have your own CPU right then and there. You don't need to actually have the CPU supplied by the manufacturer. You can manufacture your own CPU using some of the gates you have. So use half the amount of gates. You have some 500,000 gates. You need 300,000 gates to come up with a good CPU and about 200,000 gates to design your own logic. And suddenly you have a CPU plus your own custom logic executing on your own chip. That's out of your own design. And of course, you will have the problem of if you have a CPU, it is a stored program concept. You have to do some. How are you going to download the program? What does the program stay? Does it come from outside all the time? No, it cannot be. It is going to be very slow. You need to bring it closer to your platform. So it is going to be some kind of a SRAM. You'll have some kind of a RAM inside, and you're going to download it. And then the problem of you're downloading an IP which is valuable. What if the man in the middle attack and he steals your IP and all kinds of things? So, but let's go to the next slide. So this is a typical hard CPU-based FPGA. Hard CPU means that the FPGA has a CPU built in from the manufacturer. So you can see the red portion is the FPGA fabric. In the FPGA fabric, you have those about 150,000 logic elements. This means that you have 150,000 gates. You can connect them up and have your own circuit. And apart from that, on the top side, on the blue side, you have a microcontroller subsystem, which is pretty powerful, as I can see. I mean, it's the ARM Cortex M3, which is AHB bus, which is a semi-blocking multiplexing bus, and it is having a host of different ways to communicate to the outside world, like JTAG, SPI/IO, multi-user IO, MSIO, and whatnot. On top of that, you have a DDR circuitry, dynamic double density RAM. So these are powerful stuff. And why are we at all thinking about this kind of things? I mean, you have the capability to do stored program execution there. A stored program execution means that you can write code and download there and execute it by the FPGA. So it's not too much different from a CPU memory subsystem where you develop your code and download in there and execute. So that's what is raising some concern, at least in some corners of the IV&V, that these things are getting way too complex and becoming way too capable, just like a CPU memory subsystem. I mean, would you do IV&V on the radio portion of your network? Well, if it is running on a Spark processor, has its own CPU memory, yeah, many times we do it. Would you do IV&V on an FPGA that has a CPU in it and has some executable code? Why not? So let's go to the next slide. So here is an FPGA that doesn't have a CPU, but it is radiation hardened, has lots of gates, and it has some dual port static RAM, and it is a number of different things. This is a typical RT Pro ASIC 3, which is used quite a bit in spacecrafts. Okay. And this is radiation hardened. So no wonder that NASA and many other space agencies, they use it. So I'm just giving you an example that this is a pretty simple looking stuff like RT Pro ASIC 3, but the amount of gates that it has could be pretty high. It could be something like 500,000 or close to 1 million gates that you have. How many gates you need to have a good CPU? No more than 300,000. I mean, your Pentium chip, it probably has 1 billion gates. Okay, but that's too complex. But we don't need billion gate thing. I mean, I'll get a good CPU done within about 300,000 gates. And these FPGAs will give you those many gates, and then plus some for your own logic. So what are why people do FPGA? I mean, FPGAs are faster. The signals that come in, they don't come in one line. They are coming in multiple lines. They're coming in multiple lines, and I have the capability to handle them all at the same time. Signal coming in, I handle it. has special circuitry. Signal coming has special circuitry, circuitry. So all these circuitries, they're going on all at the same time. So that's why it is faster. Compare that to a CPU. CPU, how much CPU can you put to actually make the thing faster? Maybe 4, 8, no more than that. I mean, modern day CPUs can't give you any more than say 4 cores with 8, with each doing about 2 hyper-threading, and so about 8 cores. Not really cores, because they are sharing components. Like ALU and FPU, they are being shared within each core. So things like that. So your advantage of using the FPGA comes in the form of being able to do highly parallel processing. That's number one. Number two is that you can offload your standard stuff. Does the CPU need to be bothered every time when a TCP/IP packet comes in? It has been coming the same way for the last 50 years. Just put it up and put it there in the memory and let that be processed. So those are the standard things that you can get it done by the FPGA, like 1553 bus. For the last 50 years, it hasn't changed, so why not put that same thing into that FPGA? We'll be all happy with it. Okay. How much power does it take? For that same CPU and FPGA, if you do compare, you'll see that FPGA is about the same, and typically it is less. Even though it is doing things in parallel, it will be less. And what kind of speed can you attain with these things? It is as fast that it's fast enough that you can put it on missiles. You can do DSP-based signal snooping, like you go close to enemy territory and try to listen to what's being talked about and things like that. You need a lot of processing power and very fast signal processing capability, and FPGA will be able to do that. So some of these properties actually make the FPGAs pretty attractive for your spacecraft application, and IV&V, for the last few years, they are seeing quite a good number of these FPGAs. Like right now, the Mars Science Laboratory project, it is using the FPGA to wake up, get its battery charged, and sleep, and all those things. So when that Mars Science Laboratory is actually sleeping, who is actually in charge of the thing? That FPGA. There is a dream mode FPGA. You can read it up. There is the pointer there. EE Times has a very nice coverage of that same information that I'm presenting here. So once again, so there are some compelling reasons that you should be concerned about the FPGAs, at least the ingress of in so many different areas, that FPGAs are really becoming a kind of thing to think about, that there are too many of them in different areas. I can justify my statement by these famous software engineering requirement documents, which is publicly available. That the slide shows the pointer. Here it says that everything that's actually called software, government, off-the-shelf, mods, and everything is software. I mean, you execute a logic and it becomes a software that looks like it. It is that expansive, that definition. But note that it actually doesn't define what firmware is. And so when you use the word firmware, it does cause some discomfort among us. People who are actually used to a more traditional environment where there is a PC or a workstation and you just work there and you don't really bother about what's going on in the background, you know. But that assumption kind of not very good in a spacecraft environment, because in spacecraft you are actually executing control software using lots of embedded components. Those components, you've got to know a little bit about it before you actually write your first line of code, you know. So this is the reason that the spacecraft applications, they do involve some kind of a lot of kind of software firmware kind of interface, and in between area where a lot of code is present, either in the form of FPGA or in the form of driver and low-level interfaces, and we need to be aware of those areas. And I see a tendency of the high-level code being actually pushed down more and more towards the FPGA area. And that's the concern that we're trying to present here. I think that's my control over to John. You can take it.
That's okay. I'll just use this. Nah, it's okay. Can you guys hear me? All right? All right, thanks. This is kind of our transition slide here. That was the exciting part of the presentation. So just in general, the rest of it's kind of just a thought process of how we might consider scoping analysis toward a standard FPGA, which might be less exciting and attractive to potentially something more where the developer actually does consider using the CPU. Generally, our focus for IV&V has been in the software boundary. We would look at anything from well, the whole set of applications all the way down to the operating system potentially. However, we'd also look at the interfaces to firmware and hardware that's in the subsystems. The difference here is we'd have to start thinking about if IV&V does start performing analysis into the FPGA type world, you have to start considering other additional interfaces and what the CPU does with the inputs to those MOSFETs and other electronic logical circuits, as well as what its purpose is with respect to interfacing with the hardware. Right now, that would be considered something that we would normally consider out of scope. So basically, just a general process of our project was looking at some FPGAs. There was about maybe 20, 21 FPGAs that we found in a set of mission PDR type slides. Prior to that point in time, we didn't find any other references. I believe that's pretty much the earliest point in time of a project that you're going to find references that describe an FPGA, not just the types of FPGAs that are there, but the actual schematic that they're using, so that you can do some research on specifically what is involved in that specific FPGA. You might find out with some of those models that there is actually a CPU involved, and that's where the heads start turning of, well, this might be a possibility for us to consider looking into, to really define what is the project using it for. Are they just keeping it as standardized that was developed by the project, or are they actually developing internal code? So once you find the documentation, once you identify what FPGAs might exist, the next step is really to fully understand that. You might not have enough knowledge on that until you get towards CDR, or you start receiving some of the ICDs that talk specifically with the software and further knowledge on what exactly that FPGA's purpose is. Our step, what we tried to do was correlate the FPGAs to our portfolio-based risk assessment. It's really the first step to kind of realize if the main drive of the FPGA is supporting a purpose that is not in scope from at a high level capability that describes what the mission's purpose is, then you can basically filter it off from that point. The next major step is, when you're identifying what the purpose is, to describe in some sort of means what the project has defined as their heritage and how they're using it. And the last step would be to filter, if any FPGAs are actually in scope, would be to consider performing an actual RBA as if it was an entity that we considered in scope. So some of the criteria for guidance that we were considering, again, capability, first measure of a filter. Does it support something that is considered mission critical for your project that you want to perform analysis on? And then the more interesting areas, you start considering the heritage of the FPGA itself. Is it something that's serving a standard typical industry type 1553 or Ethernet? Is it supporting space wire? Is it utilizing the specific FPGA as is? That's something that has been fully well tested. It's something that its documentation is available. The project is going to consider itself as a black box, and it's not going to be any interest to us. However, there might be an area where they actually do describe that they're actually making specific plans to develop code and or firmware of such that might represent a set of state machines to perform specific type of functionality. On our current project, they're developing a new FPGA to support a processor redundancy mechanism. In those kind of cases, you're probably looking at something that is first time and or at least something that has been never considered before. It's only being used on this project, hasn't been tested. That's something of an area that we at least want to consider performing some sort of interface analysis and at least a procedural type check. Are they in line with your standard NASA standards? There's a possibility that they're reusing something that is not specifically OE, is not considered industry standard. It was developed in project in-house and has been utilized for one or more missions, but they're making high changes for it, something for a specific instrument, something for a new part within the processor. The next criteria that we can think about is whether or not they are actually making plans to do any changes in this area. Are they developing something from ground that will be just tested on ground and then never made changes to? In that kind of case, we may, again, decide to filter that kind of analysis out if the purpose of it is a one-time only, but no changes are planned. Typically, I would say from our, I guess, analysis of what was of focus for us, maybe 80–90% of all the FPGAs that we looked at provided basically just a standard type logic implementation that did nothing more than your basic command and parameter updates. There was no code looking at it, but we had one or two cases where we were interested in looking further into it. So this slide is basically just to kind of ponder on the fact of if we did perform analysis on an FPGA, what kind of concerns would we have as an organization? What type of limitations would we have to consider when performing the work? We're not gonna have the expertise or time at this point to, neither as a project, to test everything. You're going to want to limit things that are specific to supporting that firmware that was attractive to you. We're going to have to develop either in your project or as an organization further knowledge on the standards of FPGA development and the competency of just understanding what the basics are of being used for your project. One of the concerns that we're going to have across the board, whether we do support analysis and starting from potentially requirements, although most likely we're going to be out of phase by the time we have we receive any of those type of artifacts for an FPGA. You might get into a situation, and many projects have, where the projects themselves are not willing to provide those artifacts, and depending on the criticality of the FPGA and how it correlates to our PBRA, there might be a need to write a risk and further consider opportunities. With requirements analysis, you're most likely, if we performed any type of analysis, there's not going to be any traceability provided. There's not a requirement to perform traceability down to that level. You might be limited to supporting just a general quality check and procedural check of, are they considering all the inputs and outputs for an FPGA, basically treating it as a black box. Similarly with the design, we most likely will not receive all the artifacts. But if you do, there's always the possibility that we could actually develop our own house MATLAB or Simulink that can help test, in the future. Especially if we're looking into software that's developed with if we get into implementation, there hasn't been a whole lot of experience in this organization for the type of language that we'd have to look into. So we'd have to determine whether or not it was worth the time and effort to first learn the language before even performing the analysis. And in the end, we might be just limited to performing test analysis. And that test analysis, again, will still have the same concerns, but at least we can consider performing normal IV&V based on the test results and what the expected inputs and outputs were. That's really all we have. I guess there is a summary page. So in summary, we're seeing, at least on each project, that there is a possibility, there's a growing possibility that there is at least one or more FPGAs that should be considered for IV&V to pursue. And the presentation was just a kind of an attempt to show how you might consider what those FPGAs are, and the next step would be basically to describe how you would perform and what you would perform FPGA analysis on. Any questions?
I do have a question online, actually. How do you add value compared to the debugging tools provided by various FPGA development design tools such as Synopsys toolset? Good FPGA design practices and methodologies and rigorous testing. So how do you add value compared to debugging tools already provided by FPGA development design tools and given design practices and methodologies and rigorous testing?
Actually, what I would suggest, at this stage not to go too far deep into the FPGA guts like VHDL and those kind of things. I mean, it itself has a lot of design checks coming out of the standard VHDL development process. What you need to do is that you need to make sure that whatever you have done inside interacts well with your with the logic that it is supposed to interface outside. So at this time, I would suggest that you treat it as a black box and understand the states. That if it is supposed to wake up a CPU, it should go through a various state transitions. You should expect a detailed list of state transitions coming out of it. How many times do you see a state transition very well detailed coming from the developers? I would be suspicious that not many times. So we should be demanding those things. So without that, you don't know what's happening. You don't know how to interface with that FPGA. So it is the interface, that's the problem, that's the area that we are trying to focus on to get started with, okay? Because that's the area of concern. Inside the FPGA, you're right. I mean, there is a lot of already good development checks that are being done within the FPGA development process itself, but on the outside part, the interface part, that's a problem area in our point of view. Does that answer your question? I hope so.
Let's see people's response, and while we'll take other questions in the room.
1, 2, here we go. Are you aware that we did do sort of an emergency Tiger Team FPGA analysis on Juno I wouldn't say many years ago, but it was a few years ago. And Sam Brown was part of it. I tried to text him to get him up here, and I don't see him. But basically, it was a case of they had left diagnostic logic in the FPGA for their bench tests, including I think like writing output to some device for debugging, and then that was left in, and that flew, and so that became a problem. And so certainly they didn't find that with a debugging tool because it probably wasn't broken when it's running on the bench. But that seems to me like an opportunity for external review to look at, certainly like question 2, right? Doesn't do what it's not supposed to do.
Yeah,
You shouldn't have an FPGA right into a teletype device or something like that. I mean, you could if that was its purpose, but I wish Sam were here. But we definitely did some work, and it was very short string, and we had to get smart on VHDL. So I definitely recommend you get in contact with Sam for that, because there was an effort. That was a few years ago.
Okay, thanks for the input.
Okay, thank you guys.